Welcome back. In this section, we're going to start looking at limits again, this time limits as x becomes infinitely large, either infinitely large in the positive direction or in the negative direction. This is because very shortly we're going to start looking at curve sketching, and so we need to be able to talk about what's happening at the far left and far right of our graph. What is the end behavior of that function? So what are these limits at infinity for the function f? So if your limit exists, if we have that the limit as we approach infinity is some real number, then it means that however close we'd like to be, so here this is again kind of an epsilon definition of limits. So however close we'd like to be to that limit, provided we are big enough for x values, provided that x is further enough to the right, our function will be close enough to that limit. Or for the reverse, if we're talking about a limit as we're going to negative infinity, provided that x is small enough, our function will be close enough to our limit for however close we'd like it to be. We're not going to be using the formal definitions, though, for limits. We're going to be using a couple of theorems to help us out, and then some ideas from earlier. So a couple of things, though, just as far as the implication of this and getting into what does it mean for curve sketching later on, when we're saying that the limit as x goes to infinity of our function is some number, or as x goes to negative infinity is some number, that's telling you that your graph, f of x, has a horizontal asymptote, and that's the line y equals L, and that it's doing that horizontal asymptote on the left side, sorry, on the right side, or the left side, or potentially both. And that's another thing to keep in mind here, of course. You have two sides, a far left and a far right. It's possible that your function has the same horizontal asymptote on both sides. Maybe it has two different horizontal asymptotes, one on the left, one on the right. Maybe it only has one horizontal asymptote, it's only on one side, or maybe it has neither. But those are really the only options that we have as far as horizontal asymptotes. The good news, as I say at the bottom, most of the properties for limits that we learned at the start of the term will still apply here when we're looking at these limits at infinity. So the important theorem that we're going to use here, this limit at infinity, is telling us that if we've got ourselves some power, and the power is some sort of positive rational number, so the x that's in the bottom is in the bottom of this fraction for real. It's not just sort of secretly pretending to be there and this is a negative power, but really secretly the x is up top. Not like that. We've written it so that the power is a positive number, so x is legitimately in the denominator. The constant up top, this constant c, could be any real number we'd like. It doesn't really matter. So if x becomes infinitely large, then that kind of an expression will get close to zero. And if we're talking about the negative side of things as x goes to negative infinity to the far left, provided our little function here is defined for negative values, then yes, that limit will exist and will also be zero as well. You have to be a little bit careful about that, thinking about does that function exist. So if our function was 1 over square root of x, for sure, as x goes to infinity, 1 over root of x will go to 0, and that's courtesy of the theorem that we have above. But if we were looking at limit as x goes to negative infinity, I would say that that does not exist. And that doesn't exist because our function, 1 over root of x, is not defined for negative values of x. So if your function was defined for negative values of x, then yeah, you could go right ahead and say that as x goes to negative infinity, that fraction would go to 0. But we have to be cautious. There are lots of cases where maybe our limit as x goes to negative infinity won't exist, and that's because our function isn't defined. And again, the same little caution that we had before, indeterminate forms, when we have things like 0 over 0 or infinity over infinity, or even things like infinity minus infinity, or 0 times infinity, all those things are indeterminate forms. And that means that we have to do something further to be able to evaluate our limit. So let's find some limits. The first one is the most straightforward one, because for this one, as we're looking as the limit as x goes to infinity, I can say, well, I've got 3 terms, and for each of those terms, I know what's happening as x goes to infinity. As x goes to infinity, 3 is going to stay as a constant function 3. And that's because from before we had our limit law for constants. The limit of a constant is the constant, so the limit of 3 is 3. And from our previous theorem, 2 over x and 5 over x squared, those will both go to 0 as x goes to infinity. So this is not indeterminate at all. It's 3 plus 0, which is just 3. Now, on the other hand, if we're looking at the denominator and looking at what happens as x goes to negative infinity, on the top, negative infinity is going to be winding up getting squared. It's going to be some sort of positive infinity going on up there for the numerator. Down below, I've got infinities being cubed. It's going to be some sort of negative infinite number. It's infinitely large on the top, infinitely large on the bottom. So I need to do something because, of course, infinity over infinity is indeterminate. So my plan here, I'm going to take this expression that I have, and I'm going to divide everybody top and bottom by my largest power of x. So here, the largest power of x that I have is x cubed, so I'll divide everybody top and bottom by x cubed. And then we'll see what happens after I've done that. So after I've done that and I simplify just a little bit, I'm going to see that I've got something where all the individual terms, I can evaluate them, and none of the terms are infinity anymore. And that, in fact, I can find the limit for the numerator and the limit for the denominator. So if you're looking at the limit for the numerator, I have 2 over x, that'll go to 0, 1 over x cubed, that'll go to 0. And in the denominator, the 1 over x cubed, the 3 over x, they'll also go to 0, and the 1 will just stay as a 1. So for the numerator, it goes to 0. The denominator, it goes to 1. So since the top has a limit, since the bottom has a limit, and the bottom doesn't have a limit of 0, then it's 0 divided by 1, which is just 0. So that's telling you that if you were graphing this function, it would have a horizontal asymptote y equals 0 on the left side. Let's do a couple more here. So this next one, I'll do the same sort of thing. I'll divide by my largest power of x. And so if I were to look at this, I would say, well, dividing by the largest power of x that I have is x cubed. So if I divided everybody by x cubed, I would have 5x cubed divided by x cubed, 3x squared divided by x cubed would simplify to 3 over x, 1 over x cubed. I'd have 4x cubed over x cubed, which would give me just 4. 3x squared over x cubed, which would be 3 over x, and 1 over x cubed. And again, I can see that the limit exists for the top. In fact, for the top, the limit is just 0. The limit is just 5 minus 0, which is 5. For the bottom, we have a limit, and it's also not 0. It's 4 plus 0 plus 0. So we have a limit for the top. We have a limit for the bottom. The limit for the bottom is not 0. So we can just go ahead and say evaluate our limit for the top and get 5, and our limit for the bottom and get 4 or 5/4. So that second graph, if we were to graph y equals all of that, it would have a horizontal asymptote y equals 5/4. And then for the last one, so here I'm going to have to think ahead about what I'm going to do. I know that up till now I've divided everybody by the largest power of x, but I know that if I do that here, divide everybody by x to the 7, then in the bottom I'll have 6 over x to the 4, 3 over x to the 5, 4 over x to the 7. Everybody will go to 0 and my denominator will go to 0. Remember, for me to be able to evaluate my limits, the top needed to have a limit, the bottom needed to have a limit, and the bottom couldn't have a limit of 0. So dividing everybody by x to the 7 won't really fix my problem for me. So instead what I'm going to do is I'll divide everybody by the largest power of x that I have on the bottom. I'm going to divide everybody by x cubed. So if I'm taking a look at this, I can see that when I divide the bottom by x cubed, I'll have 6 plus 3 over x plus 4 over x cubed. And for the top, I would have as x 3x to the 7 divided by x cubed is 3x to the 4 minus 2x cubed over x cubed, which is 2, minus 1 over x cubed. So now my limit's not going to, my limit for the bottom is not going to 0 anymore. As x goes to negative infinity, the denominator is going to 6 plus 0 plus 0. The denominator is going to 6. And in the numerator, I can say to myself, well, as x becomes infinitely large, I'll have 0, I'll have minus 2, and I'll have some large number that's being raised to the power of 4, which will now become positive and will be multiplied by 3, so even bigger, even more positive. The top is going to become infinitely large minus 2, which is still infinitely large. So in other words, the numerator is going to infinity, the bottom is staying constant at 6. This thing is not going to go to a finite number. This limit, we would say, does not exist. And if I wanted to say why it doesn't exist, I could say specifically it diverges to positive infinity. In other words, the y values are getting larger and larger, more positive, as x goes to the far left. As x goes and becomes very, very negative, the y values become very, very, very positive. But I don't have to say diverges to positive infinity here. I could just say does not exist, and that's good enough, because that's all we wanted to know is do our limits exist or don't they, and if they exist, what are they?